Hello? Hello?
Yes, sir.
Okay. So we are discussing Fourier series method of designing FIR filter. And in Fourier series method, what we have used is, I can specifically say that is a rectangular window. Second method, second method is called windowing method. So we can make a heading, windowing method. So first let us see today's section, not a problem here. First let us see what is the relevance of using this particular method. So even though we have Fourier series method, why we have to shift to windowing method. So we will discuss what is the disadvantage with this Fourier series method, or particularly using a rectangular window. Method and recollect the method. First you will take the inverse Fourier transform, isn't it? No. HD of e power j omega will be given to you. You have to take the inverse Fourier series so that you will get HD of n. Then you have to truncate it. Here you have the process of truncation. Here you have the process of truncation. You will truncate it to say capital N number of terms, right? And we called it as h dash of n. You call it as h dash of n, and ultimately you will shift it and you will make h of n cos L. That was the design procedure. Hope you remember this, right? This process in a graphical attempt. What is this process? So let it be my HD of n. Okay, this is my HD of n. So what is the problem with HD of n? HD of n letter terms and now
Infinity.
Definitely you have infinite terms. So infinite terms and okay, you have infinite terms. So you go for truncation. So the process of truncation can be visualized like this. You multiply the second sequence. Say for example, if you need 7 elements, say capital N equal to 7. So you will take a rectangular window from the span -3 to +3. That means -3, -2, -1, 0. All these values or sample value will be 1. Then 1, 2, and 3. So this is what we call it as a rectangular window. Rectangular window with n equal to 7. So what will happen when you multiply these two sequences? Let me call it as W of n. W of n. This is W of n. Now, what is my final result when you multiply these two windows? We have HD of n into W of n. And that is actually your h dash of n. This is h dash of n name. This is your h dash of n. So how the figure will look like? Say 1 into this particular. This will have some values according to your design, inverse Fourier series equation. So that values will be kept as such in this span. In your span, you will have those all values. See, if these were the previous values, you will get exactly that values because you are multiplying with what? 1 going to multiply n. After that, the all values will become 0. So this is what you are mathematically doing with truncation. With truncation, this they are related. Very mathematically related. How h dash of n, sorry, right here, this one, right? H dash of n is equal to HD of n into W of n. Now tell me what was W of n? Mathematically, just graphically, what is W of n here?
Truncate the signal.
And that can be called as W in the period and window. For window. Okay. So this is my window. And for this case or for the above process, which particular window has been used?
Rectangular window.
Rectangular window and multiply the terms in say 7i, -3 to -3, -2, -1. Okay, 0th sample, first sample, say second sample, and third sample. So you have -3 to 3 n equal to 7 window and multiply result. Clear ആയോ? So നമ്മൾ ഇതുവരെ ചെയ്ത പ്രോബ്ലത്തിൽ was there any window over there? Or have you done the process of windowing? Windowing എന്ന് പറയുന്ന ഒരു പ്രോസസ് നിങ്ങൾ ഇതുവരെ ചെയ്ത പ്രോബ്ലത്തിൽ ചെയ്തിരുന്നോ ഇല്ലേ? ചെയ്തു. You did it, right? Because you mathematically limited this to n number of terms. That process is called multiplying with a window, and that is referred as truncation. But truncation is a process of, you can say like this, truncation is a process of limiting the number of terms to a defined number, a finite number, with the help of a fellow called window. And specifically, you used rectangular window till now to do the problems. Clear ആണോ? ക്ലിയർ ആണോ? ഞാൻ ഒന്നുകൂടെ പറയാം. ഓക്കെ, ഞാൻ ഇന്ന് ഇതിന്റെ ബേസിക് തിയറി മാത്രം പറഞ്ഞ് മൈൻഡ് അപ്പ് ചെയ്യും, പ്രോബ്ലം ചെയ്യുന്നില്ല. അതുകൊണ്ട് ശ്രദ്ധിക്കുക, ജസ്റ്റ് റെസ്പോണ്ട് ടു മീ. എനിക്ക് കറക്റ്റ് ആയിട്ട് റെസ്പോണ്ട് ചെയ്താൽ പെട്ടെന്ന് കാര്യം പറഞ്ഞു തീർക്കാം, എനിക്കും സാറ്റിസ്ഫൈഡ് ആവും. ഓക്കെ, സോ ജസ്റ്റ് ഫോക്കസ് ഓൺ മൈ സെന്റൻസ്. ഐ എം defining you truncation. Truncation is the process of making the length of this sequence finite. How can you do that? With the help of, say, a rectangular window. Rectangular window ഉപയോഗിച്ചാണ് നമ്മൾ ഇത്രയും നാളും ട്രങ്കേഷൻ ചെയ്തത്. And this is the process that we have done till the last class. ശരിയല്ലേ? Okay, and yesterday we solved one problem and one or two problems, and you had some designs for ഇത് ഇന്നലെ ചെയ്ത പ്രോബ്ലം ആണെന്ന് തോന്നുന്നു. I don't remember exactly. So you had some h of n value, something like this. This was your design. So to complete this FIR filter design, this is an FIR filter. To complete this FIR filter design, we used a rectangular window. Got it? Now I will tell you a drawback of this fellow. ഇയാളുടെ ഒരു drawback എന്ന് പറയുന്നത് എന്താണെന്ന് നോക്കാം. So you can ഇതിൽ ആവശ്യമുള്ള കാര്യങ്ങൾ നോട്ട് ചെയ്യാം. I'm going to make a next heading called Gibbs Phenomenon. Gibbs Phenomenon. Okay. ഇതൊന്ന് ശ്രദ്ധിച്ചു ആദ്യം. See, the problem with rectangular window has a problem. Okay, the problem with this particular fellow is called Gibbs phenomenon. There is a problem, or there is a particular phenomena called Gibbs phenomenon. So with the process what we are doing, the truncation is referred as abrupt truncation. This kind of truncation is referred as abrupt truncation. So if you consider a rectangular window, I will just draw a window of size, say 5. This is a rectangular window, okay, of size 5. Say capital N equal to 5. 1, 2, 3, 4, 5 sample size. So here I am saying I am introducing you a new term called abrupt. Abrupt means what? Sudden. Abrupt truncation. That means you are making a sudden stop. Infinite terms നമുക്ക് ഉണ്ടായിരുന്നതാണ്. അതിനെ വളരെ ഫാസ്റ്റ് ആയിട്ട് നിങ്ങൾ എന്ത് ചെയ്യാണ്? ഒരു കട്ട് സ്റ്റോപ്പ് ചെയ്യാണ്. This is like something like നിങ്ങൾ ഐഡിയൽ ഫിൽറ്ററിലൊക്കെ പറയുന്ന പോലെ ഒരു ഇമ്മീഡിയറ്റ് അറ്റന്യൂവേഷൻ ആണ്. Isn't it? I need all the samples before this, and I want to neglect all the samples after this particular point. So this is a sudden truncation, or this is referred as abrupt truncation. Now I will introduce you another term called smooth truncation. Smooth truncation. This is N. I will introduce you another window called a Hamming window. HAMMING. Okay. So this window will actually look like this. ഇതിന്റെ ബൗണ്ടറി എന്ന് പറയുന്നത് you will have a shape something like this. You will have a shape like this. So here this is not a sudden truncation. Here it is sudden abrupt truncation. Here it is a smooth truncation. Gradually you are truncating to 0. You are not making an immediate stop. So one problem with this rectangular window is he is having abrupt truncation. Now you may doubt what is the problem with this abrupt truncation. നമ്മൾ ഇങ്ങനെ truncate ചെയ്താൽ എന്താണ് problem? Okay, so the problem with abrupt truncation is that if you observe the frequency response, say for example, if you are designing a low pass filter, your task was to design a low pass filter something like this. If you are using a rectangular window to do the design, you will have ripples, or you will have some oscillations in your response. Response il korchu oscillations കാണാൻ പറ്റും. This is the frequency response, say h of e power j omega. There you will have oscillations, and this phenomenon is referred as Gibbs phenomenon. ഈ phenomenon പറയുന്ന പേരാണ് Gibbs phenomenon. ഞാൻ ഒന്നുകൂടെ പറയാം. Listen carefully. I need all your attention. Till now, or using this Fourier series method, we used rectangular window to perform abrupt truncation. Is that clear? We used rectangular window to perform abrupt truncation. What is the nature of rectangular window? He has got an abrupt truncation. He will perform an abrupt truncation. The truncation is not smooth. As a result, you will have oscillations in the frequency response. Or your design like this. This is the time domain. This is your h of n. This is the time domain. If you take the frequency domain plot see if it is a low pass filter, that will be like this. You will have some oscillations in the response, and this phenomenon is referred as Gibbs phenomenon. So who is the cause, or what is the reason behind this oscillation? Or who is the reason behind this Gibbs phenomenon?
Abrupt truncation.
Abrupt truncation. The rectangular window who is having an abrupt truncation. So what is the solution to avoid this? I don't prefer these oscillations. So what is the solution to this oscillation? Abrupt truncation is a problem. So what is the solution?
Smooth truncation.
You avoid abrupt truncations and use windows who have smooth truncation. Something like Hamming window, Hanning window, triangular window, Bartlett window, different windows are there which are having smooth truncation, and that can be used to avoid the problem of Gibbs phenomenon. Clear? I will show a demo in MATLAB and I will wind up. We will do the problems tomorrow. Clarity rectangular window truncation use problem with rectangular window is abrupt truncation. Because of abrupt truncation, you will have oscillations in the frequency response. Frequency response oscillations with. This phenomenon is referred as Gibbs phenomenon, and the solution to Gibbs phenomenon is avoiding abrupt truncation and go for smooth truncation. You go for smooth truncation. This is the point note. Smooth truncation. Smooth truncation, you can use some windows. I will give you some examples. One is triangular window. Triangular window. If I draw the outline, it will be this like triangle. Okay, you will have samples like this. Perfect triangle window. Okay, this is your triangular window. Then another thing is Hamming window. H-A-M-M-I-N-G. Hamming window. Third one is Hanning window. H-A-N-N-I-N-G. Both of them look similar, or similar shape. The only difference is with one particular value. We will look that in detail. We will see that at the time. Both of them have almost same shape. This is just the boundary. Okay, it's not continuous. It is W of n, discrete and I'm just drawing the boundary. And another window is Bartlett window, Kaiser window. Different windows are available. Okay, we will focus only on Hamming and Hanning window as per your syllabus. Clear enough? I will demonstrate you the phenomenon of Gibbs phenomenon. You can use a problem.
Rectangular window use Gibbs phenomenon.
Sudden truncation. That's a design procedure. The back concept I'm not able to answer. Rectangular window abrupt truncation oscillations. Okay,
sir.
Okay. That is an observation. Okay, I think so.
Okay, sir.
Okay. This rectangle, the problem problem I think. Problem. Last. Yeah, answer one of the problem. This one. Somebody please cross check. Make it one of the low pass filter.
High pass filter.
High pass arena. Okay. Okay, so that was a high pass filter, right? Sure. So what was the cutoff frequency? What was the cutoff frequency for this question?
Pi by 4.
Pi by 4. Okay. അപ്പം ഞാൻ അതിനൊന്ന് ഇവിടെ കൺസോളിഡേറ്റ് ചെയ്ത് എഴുതാം. നിങ്ങളുടെ ബുക്കിൽ ഉണ്ടാവും. Your question was this thing, the desired response, omega and hd of e power j omega. So that was high pass filter with cutoff frequency എത്രയായിരുന്നു? Pi by 4 അല്ലേ? So pi by 4 to എവിടെ വരെ എക്സ്പാൻഡ് ചെയ്യണം? അപ്പോൾ ഇന്നലെ ഒരു ഡൗട്ട് ഉണ്ടായിരുന്നു ഇതെങ്ങനെ ഫിൽട്ടർ ഐഡന്റിഫൈ ചെയ്യുന്നത്. ഞാൻ ഇന്നത്തെ ഈ ഒരു സെക്ഷൻ ഡെമോ കഴിഞ്ഞിട്ട് ഇതൊന്ന് എക്സ്പ്ലെയിൻ ചെയ്തു തരാം ഫിൽട്ടേഴ്സ്. So this is minus pi by 4 and this is minus pi. എല്ലാവരും ശ്രദ്ധിച്ചോണേ. ഓക്കെ, ഇതാണ് നിങ്ങളുടെ കസ്റ്റമർ പറഞ്ഞ ഡിസൈൻ. He want this frequency response and you designed, right? You designed something. You designed an FIR filter. അപ്പോൾ ഇത് ടൈം ഡൊമൈൻ ആണ്, ഇത് ഫ്രീക്വൻസി ഡൊമൈൻ ആണ്. കസ്റ്റമർ ഈ ഫ്രീക്വൻസി ഡൊമൈൻ പറഞ്ഞു, യു ഡിസൈൻഡ് ദ ഫിൽട്ടർ. സോ യു ഹാഡ് ദ ഫിൽട്ടർ കോഎഫിഷ്യൻസ്. ഒന്ന് ഹെൽപ്പ് ചെയ്യോ, ഏതൊക്കെയായിരുന്നു വാല്യൂ? 0.045 ക്രോസ് ചെക്ക് ചെയ്തോണേ. 0 minus 0.075 minus 0.159 minus 0.225 then minus plus 0.75 which is 3 by 4 minus 0.225 minus 0.159 minus 0.075 and 0.045. Isn't it? This was your design. ശരിയാണോ?
Yes, sir.
Right. Now I am going to simulate in MATLAB. ഞാൻ ഇതിനെ MATLAB ഇതിനെ എങ്ങനെ MATLAB സേവ് ചെയ്യാം? For MATLAB, this is, you need the transfer function. H of z is b by a, right? FIR filter a value is always 1. What is your corresponding b value? B value is exactly this matrix. അല്ലേ? ഇതിന്റെ H of z എന്താണെന്ന് പറയാൻ പറ്റുമോ? H of z, what is the transfer function from this? H of z equal to anyone? 0.045 plus, sorry, minus plus 0 z raised to minus 1 എന്ന് വരും. Minus 0.075 z raised to minus 2 minus 0.159 z raised to minus 3. ശരിയല്ലേ? Plus minus 0.225 z raised to minus 4 plus etc. ഇതാണ് നിങ്ങളുടെ ട്രാൻസ്ഫർ ഫംഗ്ഷൻ എന്ന് പറയുന്നത്. അതിന്റെ കോഎഫിഷ്യൻസ് ആണ് ചോദിക്കുന്നത്. B is the numerator coefficient. So exactly the same matrix. This is your B matrix. Ready ആണോ? Clear ആവുന്നുണ്ടോ?
Yes, sir.
Okay. Now I am going to simulate it in MATLAB. Just a minute. To present the entire screen. Screen visible on MATLAB screen?
Yes, sir.
So I have saved the B and A values. A is 1 because it's a FIR filter. B is your numerator coefficient, which is the thing that you have designed. നിങ്ങൾ ഇന്നലെ ക്ലാസ്സിൽ ചെയ്ത ഡിസൈൻ. Okay, I'm going to see the frequency response. So FREQ Z command ആണ് യൂസ് ചെയ്തത് because it's digital. Okay, FREQ Z of B, let me run the program. F5 shortcut. See this. This is the response that I got. This is the magnitude response and this is the phase response. So what's your observation from the magnitude response? What kind of filter is that? Low pass, high pass. You have designed high pass filter, right? You design the customer the requirement. This was the requirement. And left side, right side മാത്രമാണ് ഇപ്പോൾ നമുക്ക് കാണുന്നത്. I will draw what I got. നമുക്ക് കിട്ടിയ റെസ്പോൺസ് ഞാൻ ഇവിടെ ഒന്ന് വരയ്ക്കാം. Okay. You had some ripples over. ഇവിടെ ഒരു ripple ഉണ്ട്. And it should actually come like this. But here also you got another ripple. See, this was your expectation. This is the pass band and this is the stop band. High pass filter ആണ്. Cutoff frequency pi by 2 ആണ്. Instead you got some ripple. ഇത് flat ആയിട്ട് പോയില്ല. ഇവിടെ ഒരു ripple കണ്ടു. ഇവിടെ ripple ഉണ്ട്. ഇവിടെ ചെറിയ ripple ഉണ്ട്. Here also you have ripple. You have ripples in the pass band as well as the stop band. And അതാണ് ഈ കാണുന്നത്. Clear? Here you can see the ripple. Ripple കാണാൻ പറ്റുന്നുണ്ടോ? Is it visible?
Yes, sir.
Okay, pass band ചെറിയ ripples ഉണ്ട്. Stop band there is a huge ripple. ഇത് വലിയ ripple ആണ് ഈ കാണുന്നത്. Okay, cutoff frequency is somewhere over here. So, ആ ഒരു 0.25 റേഞ്ചിൽ അതാണ് നമ്മൾ pi by 2 എന്ന് പറയുന്നത്. Pi by 4 ആയിരുന്നു അല്ലേ? 0.25 ആ റേഞ്ചിലാണ് വരുന്നത്. So that was your cutoff frequency. So this is the high pass filter that you obtained. So നമ്മളോട് കസ്റ്റമർ ആവശ്യപ്പെട്ടത് ഇതാണ്. This is what was asked and this is what you got. Clear ആയോ? So what is the reason for these ripples? ഈ ripples കണ്ട ഫിനോമിനയാണ് നമ്മൾ എന്ത് പേര് പറഞ്ഞത്?
Gibbs phenomenon.
Gibbs phenomenon. Okay. So that is because of the rectangular window that you had used in doing this design. നമുക്ക് ഈ same problem തന്നെ we will try with another window, Hamming window or Hanning window, so that you will get some another h of n or h of n value. We will do that in the next class, and we will see the same simulation in MATLAB. MATLAB will same സാധനം ചെയ്ത് നോക്കാം. Okay, then we will make a comparison, and you can clearly see that using a smooth truncation, you can avoid this ripples. Clear ayo? So let me stop this.
Yes, sir.